Right now, so bond parameters. So bond parameters, one of the important. So the question, whatever you ask, so I'll explain here also. Okay. So here is bond angle, bond length, bond energy, and bond order. Of course, we already discussed something else here, but we'll discuss one by one. Bond angle, bond length, bond energy, and bond order. Okay. Hello. So bond angle, Nana. So based on hybridization, somewhat we can say, because SP hybridization linear without any lone pairs. SP linear. SP2 trigonal planar shape, generally 120. SP3 109 degrees 28 minutes. Like SP3D, right? Trigonal bipyramidal shape, 120 and 90. And SP3D2 octahedral. So there is only 90 degrees, right? Square planar and I mean octahedral. Square, first one is square and one above one and below one. And SP3D3 pentagonal bipyramidal. So what is our bond angle in pentagonal bipyramidal without lone pairs? What I am speaking. So 360 by 5 is how much? Pentagonal. So no need to by heart. So 360 by 5 pentagonal, right? By 1 is 90. So in this case, Nana, angle between two orbitals containing bonding electrons like here. So linear. So spectroscopically determined, these are all. So we have different types of spectroscopies, you know. So what is a spectroscopy means to know the structure of the molecule. In organic cases, we have different types of spectroscopy, right? You know, proton NMR, right? There is number of protons in case of organic, T13 NMR, right? So UV spectroscopy, IR spectroscopy. IR means infrared. There is we will find out number of functional groups. UV means unsaturation. Mass spectroscopy, total mass of the molecule. So given data is like about the shapes. So hybridization, percentage of S character increases, bond angle is also increases. So this is one of the important point, and that is the reason we can say, I already told you, in case of S spira, percentage of S character is how much? 50%. This bond angle is 180. For example, SP2, percentage of S character is how much? 33.3. So 120 degrees. SP3, percentage of S character 25. Right? Here is 109 degrees something. When the percentage of S character increases, bond angle is decreases. Right? SP3 109 degrees, 28 or 5 we could say. SP2 120. So of course SP, it is 50%, right? 180 degrees. So write this point. Percentage of S character increases. Sometimes they are asking the question statement wise questions. Earlier I used to teach only the important areas, but each and every point in the chemistry nowadays, even JEE also, they're asking very easy questions only, but a lot of students are, you know, they're unable to solve. Next one, steric repulsions. Second one is steric repulsions are increases, bond angle also increases, right? Same center atom in the second period, same hybridization. The side atoms in the third period is like this. So this is important. For example, OF2, OCl2, right? OBr. Okay now. So all are having the same hybridization, right? Earlier I told you based on hybridization, but factors are important. So here is 103, 110, 112 means size, because fluorine, chlorine, bromine size is, right? Steric repulsions are increasing. Here is bromine size is bigger, right? Chlorine, bromine, it is by default that only it's indicating inversely, right? If the size is increasing, top to bottom, what exactly happens? Size is increasing. Bromine size is more, right? Steric repulsions. What is steric repulsions means? If the size is more, bulkiness. A lot of people are confusing steric repulsions. Sir, what is steric repulsions? What is steric? Steric means bulkiness. This is the second point. Then, so even write it down these angles sometimes. This is 103, 110. You can write, right? Next one, number of lone pairs increasing, bond angle also increasing, right? CH4, NH3, H2. This is a famous example. All are having the sp3 hybridization only, but it is having one lone pair, it is having the two lone pair. It is 109 degrees 5, 107, 104. Yeah, so number of lone pairs are increasing, bond order also increasing. So that's the reason I told you, right? Directly instead of telling. Next, Nana. So this is also important. The electronegativity of the central atom, right? So if the electronegativity of the central atom increases, right, bond angle also increases. Central atom, what I am speaking. Okay. The same hybridization, number of lone pairs also same. Oxygen, sulfur, selenium, top to bottom electronegativity decreases, right? Oxygen, sulfur, selenium, tellurium, polonium, like this in it. Top to bottom electronegativity, what happens, Nana? Decreases. Electronegativity decreases, right? So that's the reason here is same hybridization, same number of lone pairs. This type of questions frequently they are asking. So generalized statements, lot of people know, but this type of questions, lot of people are missing. Hmm. So number of electronegativity increases. Completed. Completed. Next, Nana. Electronegativity of the same side, right? So here is C, phosphorus in all the cases, but electronegativity, right? Electronegativity side atom is increases, bond angle is decreases. This is same. The point is because we know if the size is increases, automatically electronegativity what happens, right? The first statement which I gave you, that exactly you told, right? The same thing. Yeah, write it down. Right? Same central atom, same hybridization, same number of lone pairs. Same number of lone pairs. So regular geometry, all side atoms and identical, there is no lone pairs of central atom, bond angles are not affected by the electronegativity. I already told you this is the beginning of the, all the side atoms are identical, no lone pair of, right? So chlorine examples, so all the cases, all central atoms are same, right? Chlorine, 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 chlorine cases, same. TCl4, SiCl4, GeCl4, very important point. Yeah, that's only right. 109, 109, 109. And there is no lone pairs. So this point we need to understand. All side atoms are identical, okay, and no lone pair of central atom. So bond angle is not affected by the electronic. So these are all carbon, silicon, germanium, tin, or belongs to carbon, silicon, germanium, tin, lead. So same group. No, electronegativity top to bottom decreases for the central atom, but side atoms are in all the cases, and no lone pairs, because these many points are affecting, not only single point. Done? Next, no, back bonding also one of the important point. Side atom to central atom, right now. In this case, back bonding is there, right? Write it down, back bonding. So the fluorine is having the lone pair, that lone pair boron vacant p orbitals. Boron is having vacant p orbital, yes or no? Yes. So it's giving like back bonding is possible here. So in this case, nitrogen have the lone pair, silicon is having the vacant d orbital. Side atom to central atom. This is side atom is giving to the central atom, whereas central atom nitrogen is giving to the side atom. Back bonding. Yeah, if they are having the vacant, then only it's possible. Because silicon is having the vacancy in d orbital, boron is having the vacancy in the p orbital. So due to back bonding, what happens? No, bond order is increases, but net effect in the repulsions is 0. So the bond angle is 120 degrees centigrade. So in SiCl4, in BF3, what I am speaking is, in BF3, 120 degrees centigrade. Due to back bonding, bond order is increases. Why bond order is increases? Due to back bonding, bond order is increases. Obviously, right? It becomes double bond. Yes or no? Here is actually it was a single bond. Because of back bonding, double bond. When the double bonds are increasing, automatically what happens? Bond order is increases. So this type of questions are seems to be very narrow, and we know those questions. But when we are in the examination hall, so whenever we are studying, we need to think that we are present in the examination hall, in examination stress. So how they can ask the question in the particular point, we need to think in a different angles, not like, the point is there, so we studied and we mugged up. So that won't work. We need to think in different directions, how many ways they can ask a question. In this case, for example, if because of back bonding, so the bond order is increases, or because of back bonding, the bond order decreases, the statement 1 they'll give. So right now we are discussing, that is fine. But whenever we are present, sitting in the examination, because lot of points, lot of stress, that cases it won't strike. Point is easy. Everything we know. So once we are coming out from the examination, I know this point, but we could not do in the exam. Why? Because there is a hurriness is there, stress is there, anxiety is there. We need to time bounds. We need to solve other questions. In this pressure situations, a lot of people silly points also. Lots of students are doing the mistake. Recently, the same thing is happening. right? In case of N SiCl3 due to back bonding, no, so hybridization changes from sp3 to sp2 because double bond. So the bond angle is increases. And this point is also in this particular case, hello, N SiCl3 because of bond back bonding is hybridization is changing. True or false? Because right now it's fine. In the examination, we need to reproduce. That is the important thing. Next, Anna. So next is bond length. The bond angle we discussed right now. Okay. So in case of BF3, cross check. Normally BF3 is sp2. No, not changes. BF3 by default sp2, right? BF3. Hey, what is the BF3 hybridization? 1, 2, 3. 3 electrons. P2. Already sp2 is there. Double bond is there or not? sp2 is right. Next, Nana, bond length. What is the bond length? Two atoms are there. Imagine two atoms. The equilibrium distance, Nana. Right? So the equilibrium distance between two nuclei of bonded atoms, right? Of the molecules. So factors affecting the bond length. So it is very, very important. Write it down. Sorry. Size of the bonded atoms, multiplicity of the bonds, of course we know, percentage of S character, number of lone pairs on bonded atoms, electronegativity difference. Which of the following statement is true regarding bond length or bond order? They'll ask this. Size of the bonded atoms. This is very important topic. Frequently they are asking the questions. You can take screenshot even. చల్లగా ఉందా? అది నీకే సైడ్ వస్తుంది. డైరెక్ట్గా నీ మీదకి వస్తుంది. డన్ అన్న. That already we know CC single bond, CC double bond and CC triple bond, right? We can easily break here CC single bond, double bond. Bond is bond energy. What is bond length? CC bond length. What is CC bond length? 1.54 angstrom. Here is 1. 1.34 33 or 34 1.20 angstroms. So 347 611 837. The amount of energy required to break 1 mole of particular type of bond between two atoms of gaseous state in kilojoules per mole, we could say that is bond energy. So bond energy for any molecules will take it is 1 mole only. Multiplicity of bond increases, magnitude of bond energy also increases. The more number of bonds are increasing automatically. So that's the reason in case of nitrogen, in the gas is almost 78% because of nitrogen is triple bond. Right. So bond length, right, decreases, bond energy increases. The number of multiple bonds are increasing automatically. What happens? So in this case, this is, write it down. Chlorine, chlorine, Br, Br, iodine. So what exactly happens? Iodine cases, what happens? The bond length is increases. Size is more, right? Yeah. Automatically. But in this case, fluorine is having the some exceptional cases. Write this one. Wherever the exceptional cases are there, so automatically they are asking the question. Chlorine, bromine, fluorine, because of fluorine. Due to lone pair repulsions, exceptionally weaker than second period elements. This point is very important. In group 15, 16, 17, 15, 16, 17, write this point down, write it down. Even that is comes under periodic table also. Second period elements are exceptionally weaker due to lone pair repulsions. Chlorine, bromine, fluorine and iodine. Then so larger the bond enthalpy, obviously that would be stronger the bond. Polyatomic molecules, enthalpy needed to break the bond, so it's different. In this case, hydrogen gas 435, whereas in case of oxygen 498 kilojoules. In poly cases, automatically double bond is coming, right? The stronger the bond, of course, write it down. Average bond energy. So total bond dissociation enthalpy by number of bonds are broken. So even we will discuss this is somewhat in thermodynamics. For example, CH4 is given 4 bonds. We will take average. CH, 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 right? So write it down. Average means obviously total bond dissociation will be number of bonds are taking. Bond order. So the number of electrons are sharing. So number of lone pair of electrons. Bond order means 2 means double bond. Bond order 1 means single bond. Bond order 3 means triple bond. Bond order 1.5 means one sigma bond and one is partial. The partial bond means resonance. Particularly we could say the resonance of bond. So the number of bonds between two atoms in a molecule were called as bond order. So covalent bond and ionic bond, types of bonds. Covalent bond means sharing of electrons, ionic bond means transfer of electrons. Why bonding is forming, why covalent bond is forming, why ionic bond? To get the stability. Mutual sharing of electrons. So there exists some covalent character in ionic bonds, some ionic character in the covalent bond. Yes? Non-polar covalent bond, right? If the electronegativity difference is less than or equals to 0.4 between atoms. Polar covalent bond means greater than 0.4. Non-polar covalent bond, polar covalent bond. Covalent bonds are two types. Electronegativity based on electronegativity difference. That's the reason carbon and hydrogen non-polar. Right, carbon and halogen polar. electronegativity difference is more. No, that CCl 4 case is different. All 4 are symmetrical case. The dipole moment, we'll discuss that. Symmetrical electron crowd, it is H2Cl2N2, whereas unsymmetrical cases, what exactly happened? Because of more electronegativity difference. For example, try to understand HCl. HCl is a bond is like this. Imagine. Means hydrogen is giving 1 electron, chlorine also giving 1 electron. We are expecting the electron should be present in center. But what exactly happens? Because of chlorine is more electronegative. What is electronegativity? The tendency to attract the paired pair of bonded pair of electrons towards itself. In this case, actually originally this is like this. The electrons are moved towards the, then obviously we can say this is partial positive charge, partial negative charge. Partial positive charge, partial negative charge. When the partial positive and negative, 2 poles are coming, right? 2 poles, nothing but dipole moment will be there. It's the same thing we could discuss. Polarization. That's only polarization. Because of the more electronegativity, the electrons moves towards the chlorine side. Right? Due to polarization, charged ends acts as a electric dipole. Dipole moment. Dipole, 2 moles, because of electronegative difference, one is positive pole, one is negative pole. So 2 poles are forming, that nothing but dipole. The dipole moment is a measure of the separation of charges. One is positive charge, one is negative charge. Separation of charges between the 2 ends. So it's the magnitude, right? Dipole charge into products of charge into distance. Nu is equals to, right, the charge into distance. It's a vector quantity and denoted by nu. Nu is equals to charge into directions or electronegative. Q into D. So nu is equals to dipole moment, distance between separation, magnetic moment, ESU. Dipole moment. So particularly chemical bonding periodic table should be very strong. So half of the inorganic chemistry purely depends on periodic table, not half of, more than 70% of periodic table purely depends on periodic table and chemical bonding. And chemical bonding, everyone, the people who are studying the chemistry, because total nothing but bonds, right? Should know the types of bond. Right, direction and representation. So it's represented by the small arrow, the tail and head pointing towards the more electronegative center. So this point, chlorine is more electronegative. This point out will say like this. This is tail, this is head. That right. Diatomic molecules, polyatomic molecules. Difference in electronegativities, diatomic, polyatomic molecules, bond dipole and spatial arrangement. So the spatial arrangement is also important. Dipole moment. For example, when 2 people are there here, so one is imagine one is pulling this side, right side, at the same time the same energy level person is pulling left side also. which direction I'll move? The direction also important. One is moving, one is pulling this side and one is pulling this side. So I can move somewhat forward. The direction, spatial direction is also important. We'll discuss that. Dipole moment. Diatomic molecules, depends upon difference between the electronegativity and bond length, of course. In polyatomic molecules, dipole moment depends upon bond dipole and spatial arrangement. Right now, that only I told you. So the resultant dipole moment. So write the formula here is in the theta means the angle. In which angle? If for example in the 180 angle, if they are right 180 angle, so means straight linear dipole moment would be there. But in this case, write the formula. R is equals to PQ, P square plus Q square plus 2PQ cos theta. Formula telsa. Right. Dipole moment generally Q dipole, right, dominant factors. If the electronegativity difference increases, charge increases, automatically dipole moment is increases. For non-polar molecules, net dipole moment is 0. For polar molecules, not equals to 0. So write this point. Electronegativity difference increases, charge also increases. When the charge increases, dipole moment is also increases. Homodiatomic molecules, net dipole moment is 0. Heterodipolar, homo means same, hetero means like HCl, polar. Polyatomic molecules, bond dipole and spatial right arrangement, right. In this case, I told you, net dipole moment what happens? 0. There is electronegativity difference is there, but what happens? Yeah. So it can be 0. Two oppositely acting bond dipoles or cancel each other. That's only I told you, when both are, one is moving this side and one is moving this side, automatically total net dipole moment is 0. So regular geometries now. So the all hybridizations generally SP, SP2, SP3, SP3D, SP3D2, SP3D3 without lone pairs. If the spatial, right, regular geometry, we could say net dipole moment equals to 0. Regular geometries means without any lone pairs, regular geometry. Lone pairs contributes the dipole moment, but contribution cannot be quantified by the, so dipole moment is equal to symmetrical molecules. Dipole moment is not equal to 0, unsymmetrical molecule. Dipole moment is equal to 0, symmetrical molecules. So magnetic charge of electrons. So electrostatic 4.8 into 10 to the power of minus 10, right? Electrostatic units are 1.6 into 10 to the power of minus 19 coulombs. 1 dB is equals to, write that points, 3.33564 into 10 to the power of minus 30 cubic meter, coulomb meter, and this is electrostatic units centimeter. So while solving sometimes in the numerical cases. Yeah. Predicting the geometry of the dipole moment. CCl4 tetrahedral, sp3 hybridization, no lone pairs, dipole moment equals to 0. Here is also sp3 hybridization, right, 0. Here is also Nana. In this case, what exactly happens? All atoms are different. So dipole moment is, net dipole moment chloroform is 104 dB. All are having sp3, even though it doesn't have any lone pairs. That also we need to consider. And one important thing next, which I'm going to tell in the next slide. Yeah. CD3F, CH3F. So CD3F is more than the CH3F. And try to remember, carbon hydrogen bond is somewhat, right? Or carbon deuterium is somewhat less, less bond length. Carbon tritium, very less, like, got it? Hydrogen bond more, deuterium somewhat less, tritium is very less. Attractions, that nuclear attractions based on atom, right? 1 1 1 1 2 3, this is number of nuclear charge also is there, right? Hmm. Right, one, that's the reason, that's all I'm telling, right? Isotopes, this is giving somewhat more. So ortho dichlorobenzene, meta-dichlorobenzene, para-dichlorobenzene. In case of para, opposite direction. So there very less, zero approximately. It is meta and ortho. In ortho case, more somewhat meta, para, opposite direction. Dipole moment. Cis trans cases, what exactly happened? Dipole moment is not equals to zero. It is the, and one more important thing here is, right, in geometrical isomerism I used to say, right, that point, dipole moment is directly proportional to polarity. Dipole moment is directly proportional to boiling point. Right, these 2 points. If sometimes cis and trans cases, if they are asking boiling point, which is more boiling point? Which is more boiling point? This. Which is more polarity? This. Which is more melting point? Trans. Right. Dipole moment cis greater than trans. Polarity cis greater than trans. Boiling point cis greater than trans. Melting point trans greater than cis. Because of close packing structure. Why trans are more melting points? Because close packing structure. Both ends are different, so close packing is possible. In case of cis, close packing is not possible because the same side. These 4 questions, this 4 is very important. Okay. Effect of, I already told you, right? Dipole moment is directly proportional to boiling point. If dipole moment increases, boiling point is also increases. So boiling point of cis greater than trans, I already told you. Okay. Generally, percentage of ionic character, no? So dipole moment observed by theoretical into 100. Observed dipole moment and write it down. Theoretical means assuming 100% ionic character. You know? So covalent character in ionic compounds, that is but polarization. Polarization. Right. So what exactly this polarization, polarizability? Which is more ionic character? NaCl, KCl, RBCl, SCl. So which is more boiling point, they'll ask. It is otherwise which is more ionic bond, ionic character. Okay. Which is more which is more ionic character. Right? Cesium. Top to bottom. At what for example, strong ionic bond, what we need to have? Cation size should be large and anion size should be smaller. So that case a strong ionic bond is possible. Okay. So more ionic character. If cation size is small, if anion size is large, more covalent character. What exactly happens? The electron crowd moves towards the hmm. Hmm. Achieves our solutions. Yeah, 2 minutes now. 2 minutes.